my name is Kevin Kawchak. I'm the founder and CEO of Chemical Q Device, here for event seminar 131, Thursday, April 18, 2024. And this is going to go over drug discovery, generative AI, end-to-end de novo proteins, and also with tensor networks at the end there. And what you see on the screen here is basically a representation of what's going on with the paper. So you could see, so curate the protein unfolding data set is more common, right? So this is the common part. And the way this is done is one end is held still, and then the other part's allowed to waggle a little bit. And then that force required to unstretch it is plotted in a diagram. And then the generated proteins are trying to match what that plot was. And that's what the gist of the paper it is. So that's the next part here is the generative part. So the pre-trained protein language model, I think it's ESM2, it's like a Facebook development. And the new part that they addressed with this, the force and this mechanical stretching force, which is thought to be harder to achieve on the research side than just, getting the secondary structures. That's what was kind of like novel with the paper. I think at least two others did it, but they did it in a specific way. So this is done with sequence analysis. And then afterwards is basically this low right-hand corner. I'll show you some of their charts of what they did. And basically, like I said, it's like, it generates this force diagram. And then the generative AI part of it is basically having the proteins, whatever sequence that is, they use 99 amino acids. That's supposed to match up with this red line with the blue results. So basically, in a nutshell, this is what this paper is. So they call it force gen. So the force stands for this mechanical stretching force of a protein. And end-to-end is basically that, you're starting off with these data sets, and then basically the property to sequence is with the property, you want a specific pulling force, and the sequence is what Gen AI produces. Okay, so the authors previous did this with secondary structures. So these are, so primary structures are one-letter codes. Secondary structures are like alpha helices, and then also beta sheets, those types of things. So they previously accomplished that. Now, what made this one in specific, where I was able to further develop it, is basically they have notebooks up for the previous one. I wasn't able to get their secondary structure to work right away. It's probably fixable. So basically, there's notebooks up for the previous paper, secondary structures. There's a notebook up for, this Python notebook for the mechanical stretching end to end. So it's probably the longest notebook I've dealt with thus far. And so you can also get unfolding energy, mechanical strength. And the big thing is this unfolding this force separation curve, which they'll show, and then I'll show again with the generated proteins that I was able to do. And, just a nutshell, if you're coming from different backgrounds, is basically you need some training data. And the training data actually, they said it came from atomic force microscopy, hence the name F and force there. And basically what that allows you to do is you have all of this data as far as what it took for specific proteins to get unstretched, the force it took. And then, so that's the training data. So then the new, is basically saying, I need a protein that matches this force separation curve. That's the new part. Or that would be like, basically your test, right? It is however close you can get with the protein to the force stretching curve. So it used common omega fold, and I also highlighted ESM2. So this is Facebook development. I believe this is convolutional neural network based. It's 150 million parameters. In the notebook, there are some things that I tried to adjust that I wasn't able to. And no matter what, if I choose like 650 million parameters, it still would result back to the 150. So that was that for that. Now, the ESM2 is actually, it uses fill mask. So this is similar to what a BERT would do, right? So I already have a BERT protein generator that, it's further developed that basically if there's a blank in a sequence, it's filling it based on what it had learned with previous sequences as well. And then for this one, The trainable part is the attention-based diffusion Gen AI model. So it's building on this previous ESM2, and in specific, with diffusion, you'll hear about stable diffusion, this type of stuff. It's not too different from GANs. So GANs generates images from random noise, and this starts off very similarly, but it's trying to get to a specific point that it's turning that random noise into like a very cohesive, sequence for a protein to match a specific force curve. So this one I know for sure uses UNets, and UNets are very common in medical. They're supposed to be one of the more stable, preferred convolutional neural networks as opposed to transformers. And it only required a very small set of data. Now, this is important because they said, whether you're doing force pull or whatever, they're saying their method makes sense because you could not always need say the largest bunch of training data would be based on like the entirety of like the proteins, we know how they fold and that kind of stuff. Well, the smaller data set, which is what they were working on, is based on these atomic force microscopy values that now you can use it as a test. You could watch the videos, and again, the main takeaway is that it's literally holding one end still, and then it pulls, and there's some waggle on the end. So I'm talking about a protein sequence, and it's not always that it goes perfectly from outside into the inside residues. It's just basically those are the two things, and it's applying force to the right direction, and then it's unfolding in a certain way. So this is basically an MIT paper. They got funding through USDA, DOE, ARO, and additional support from NIH and ONR as well. So now this is the GANs-like type thing. So on the right is actually the first protein language model, this ESM2 that you start with. And then in the middle is this diffusion model. So basically it's an iterative approach, and you're starting off with random noise, and then you're achieving this sequence. And you could see the UNet at the bottom here, in order to take that sequence and then test it again against what it was supposed to generate based on the conditional inputs, okay? So that's what's going on here is basically, in this diffusion model, denoise, adding noise, and then generating, a sequence that makes sense. Now, this is important here. Now, in the specific notebook, like I said, it's a really long notebook, and I spent a couple of days just studying it and trying to make modifications and these types of things. But I wasn't actually able to get to this specific point. So the red line is condition. So this is basically saying like, we want to generate a protein that matches our red line, okay? And the blue line is how far off it is. So the R-squared value for this is 0.76. And then I think it's the L2 is a lower, it's a relative error. So you basically want the higher R2s and lower relative errors. And you see, it's just all relative. Like it's definitely harder to do than there's previous secondary structures or some other types of end-to-end analysis where, it has some more complexity. It's not just creating a structure that has this specific secondary structure or sequence that has this specific structure. It's actually, your end product, the force, is supposed to match as close to the left as you can. Now, what they found is using alpha helixes. Those are I didn't get any beta sheets. I'll show you with my 8 generations, but those typically account for it's the most hard you're going to require the most pulling force to take those apart because those are going to be more stable, I believe, than the beta sheets. And the one on the right is similar, except that actually it's a little bit better because the R-squared value is higher and then this error is lower. Now, this is basically the crux of the paper, and I'll show you a couple of the comparisons that they did based on it. Now, the unfolding energy itself, like I said, this has been done before, and the way the methods that they use, they get this, highly correlated R-squared of 0.93, relative to proteins and complexities. And all the purple dots, these 187 purple dots, are the actual generated proteins from their model that they created that, is returned in this notebook. So they got 87 of these, and you see the blue dashed line is the visual guide.
And, it's basically the closer it is to the darker red, the higher the correlation for R squared. Now, the one on the right is actually the most important. So this is the crux of the paper. It's the maximum pulling force. So this is basically saying, if you have a specific condition input that has this specific, force diagram or maximum force, those types of things, how close to is the generated protein that output to the conditioned one. So as you can see, it's lower. So the R squared of 0.41. And, basically what that means is that, and I'll show you in the next slide here. So the 0.41 that shows up is, you'll see it here. Okay, so you'll see the first three values on the right column. And then the two to the left are their competing methods. So alternate methods, 0.09 and 0.17. So if you just stop and think about, the complexity of it is it's a lot harder than just generating a secondary structure, conditional input, and then having a protein that's, de novo, like from scratch, that's, on its own, that's close to that. Now, it's generating a protein to try to match the pulling force. Okay. So overall, I think they were pretty happy with their results. And like I said, the notebook is long, phenomenal, whatever you want to call it. But, if you look at these results, they just tended to be a lot better than alternative method 1, which is AM1, in toughness, which is the first 3 rows, in strength, which is the next couple. They lost a little bit on 2 of the strengths. And then pulling force vectors, I think they had all of them. So, the takeaway is basically, generative AI and drug discovery is an alive and active thing. And the thing that they were talking about a lot in the paper is that it's hard to do. It's hard to do an end-to-end protein generation of something challenging like this, like matching the pulling force, how much force it takes to pull the whole protein into a linear line. It's challenging, right? So, like I said, I think, and this was a Science Advance, and it's definitely worth reading, I would say. And this is February 2024 of this year. So I would definitely take a look at it. So, these are the results. And then, so basically the next part here is, if you want to start off with a notebook that just runs, it ran on the very first try. And the thing I didn't like about it is it compresses all these cells and you have to go through and hit show code. But it's a really good sign if you go to run a very complex notebook and it just runs right away. Now, a little heads up is I had some issues with this notebook that the authors put up, modifying anything else beyond the number of proteins generated. Now, the thing you have to look out for is the force curve is for what the proteins are conditioned on. It's not the actual force curve for the proteins that were generated. Okay, so that kind of threw me for a loop a little bit. So you could see these 8 generations. So it's actually pretty close. So say the diagram that they have that everybody goes to run the model, it's the same. Your protein number 0 is going to be based off the same, force core curve, this condition input that mine was, right? Because that's how the model's set. And again, with additional programming, you can probably overcome some of these other hurdles. But I had issues with epochs and number of steps, and these types of things. And it would actually print out on these 3 files in the notebook, like it puts in the subdirectories, that it was 1,000 epochs, that it wasn't more steps, but it was same runtime. If it was 100 to 1,000 steps or 1,000 to 1,000,000 steps, and same thing, I tried it for epochs too. So anyways, this notebook's good for generating a specific number of proteins based on that force curve. It's a good start. So this protein 0 is based on the one that was supposed to have the highest pulling distance, and actually I'll show you a little bit later, and it did compared to the other 7. And keep in mind they're numbered 0, 1, 2, 3, going up to 7. So there's 8 total. And then you see the second one here too. So one thing that's missing are beta sheets, and they say, in the original curves, beta sheets are typically associated with flat lines, so meaning that they don't resist much to the pulling of each in each direction. So this is the chart. If you download the notebook, yours should look just like this. Okay. So they say to be predicted. So the protein 0 on the top here is the actual generation from this, but it's not the actual curve. This is the prediction curve. Okay, so you'll see 1, 2, 3, and the thing that's interesting here is like again, like with this top one, you know, the best protein of the bunch, the one that had the highest, it's like 382, this kcals per mole angstrom, is that it literally just takes one end and holds it still, and then it like the other end, and they describe this in the paper, is that that's the one it's applying the force to. So it's not always just knocking out curves or curvatures in the protein, like the first amino acid to second, right? It's like this whole thing is wiggling, and you're basically denaturing it, right? So you see here, the 3 and 7 down below is, it makes sense, right? So these two were designed to have very zero pulling force, and you can see that with the ends. So and again, it's not always the case that, you know, if there's not much alpha helices or like resistance on the ends, that you'll have a specific, you know, this. But basically, these are more associated with random coils on the end. So when you stretch these two, which have less, you know, of the secondary structure as the first one, you know, these two were generated based on this left curve. Now, I try to find a relationship between all of this, and I actually ran, it's called ProGPT-2, and it allows me to copy the sequence that I got from this model, put it into my ProGPT-2, which is also a text generator, or which is a text generator. And I was able to get this perplexity. And so the blue and the green, they trended together. And a perplexity in the machine learning protein space is basically high perplexity means that it's not associating well with what it was trained on before. Like meaning that you know, there's some other issues there, or some misunderstandings and calculations. It's just not a strong correlation. So low perplexity, which is I'll show you in the next slide, it's preferred, right? So that means that it's training, the whatever proteins that are generated are reflecting more to the original training data, and it's well behaved. And you know, there's issues if you see with these diagrams too. It says there's low correlations a lot of times with height, with and just looking at a 3D protein structure of alpha helices. So, you know, it makes sense, right? It makes sense that, you know, perplexity goes down, you know, for all of these different, you know, 8 proteins starting with 0, as the, you know, the pulling force goes down, because pulling force is heavily associated with alpha helices, and then alpha helices, you could see that as there's less and less of them, there's less perplexity, just because it's harder to typically base off of that original training data. And then this is important. So like I said, there's 3 main files that were outputted from this notebook beyond just the notebook reports. Now, this specific one is called a PDB atom card, and it stands for protein database. And in specific, it gives you all the details. Now, on this specific one for this protein 0, which is shown here, this is only the third of the 90 of the 99 amino acids. This is only representing 3 of them. Okay, so we see methionine and we see prolines, you know, twice. And the way you can tell the differences between the prolines is the sequence numbers here. So hopefully you've been able to look at charts like this before. But basically, like N would be nitrogen, and that's the element name you can see to the right. And then Ca would be an alpha carbon, you know, and then a Cb I think is beta, and G would be gamma. And then the element symbol you see over to the right. And then the XYZ, so you can manipulate these 3D, I think it's 3D moles, something like that, pi mole, inside the notebook. And I believe that these originally, this X, Y, and Z is printed off when it generates the protein. So in 3D space, in this cube, where this, you know, protein sits with 3-dimensional spaces, it's saying for the X coordinate is 43, -8, -1. for this first nitrogen on the very first amino acid. Okay, so likewise, the alpha carbon sits at this specific one. And there's a whole other field without this called quantum mechanics, or basically quantum biochemistry. And you look at these interactions a lot closer on the quantum mechanical scale, as opposed to like this is just, everything's in 3D space. And it does give some occupancy and another B factor as well. And as a refresher, so I'm going to show in the next slide a bunch of one-letter codes. So this is where they're all derived from. If you took a bunch of biochemistry, this should be very familiar. So the thing that is different is the side chain. So with all these, I was always taught it's NCC. So N would be the N terminus, and then the middle carbon, and then the carboxylic carbon. And then when these turn into proteins, then you're condensing or losing H2O. With these, that's the reaction. But they have different side chains, and so they'll differ in hydrophobicity, length, acid base, and those types of things, and different actions. Now, as far as what was covered here with alpha helices in particular, that tends to be more hydrogen bonding between the carbonyl oxygen and then a hydrogen off of the backbone, as opposed to the R residues. But I think they can play, the R residues typically spread out like to the sides. So this is the actual sequences of them generated. So if you run this model, 0, 1, 2, up to 8, you set it to 8. So you set the slider to 8. And again, this specific protein generated is trying to match the force curve, as I mentioned before. And then this predicted pulling force is what it was going for. Right. So they actually, in the model, there's other models too. There's 11, and I tried to run the other 10 and I couldn't get them to run. Or I got 2 of them to run, but I didn't get an output. So there's more behind it. And if you're the diligent one, you can get to what you need either through, further programming, or if you need to use other resources too. So, but you see, pulling force, this is the main crux of the paper. And the other thing that I generated were these perplexity values, which I copied each of these sequences and then put them into my PROT-GPT-2, and then it returned these perplexity values. So the trend is basically higher perplexities, and this relates to a couple slides back, if it was more a higher predicted pulling force, because that has more alpha helices. And you see the lowest one was down here. So, you see this, big peak here. So the conclusions with this is basically, you have to be a little bit patient. So the model itself, they're calling this pLDM. And if you try to further dissect it, and just be very wary, I had some issues with making any other modification beyond just changing the number of generated proteins. So even if my output file said it was 1,000 steps or 1,000 epochs or 1,000,000 epochs, the times, the generation time stayed the same, which I don't believe that should be the case. So 4.14 gigs to load. So that takes up some time. And there's other installations too. And, basically it was set to V100 high RAM, which is the correct choice, by the way. And of mine that I generated around 10.7 seconds with a V100. So this is an NVIDIA GPU high RAM. I think it's 51 gigs. I'll have to double check on it, but I didn't have to use that. It was typically to do even 8 generations, nothing more than 6 or 7 gigs that I saw that it went over. Now for the A100, which is the flagship up on Colab, it does take a lot less time. Well, it does take 20% less time per protein generation. But unless you're running hundreds of thousands of these, the biggest time that you're going to waste selecting any GPU is with loading, because that has to be, you have to use that device in order to do your generations. You can't switch off a CPU, or at least on Colab. And then I calculated a cost efficiency with this is basically with the NVIDIA V100 average, and I scaled this to close to 1, 0.95. Now for the A100, 0.47. And I base this basically 1 over the scaling factor times the average time times the hourly GPU cost. And then, so this is the calculation for the V100. So 10.71 average time, 0.49 cents per hour, where the A100, you're getting a little faster, meaning that's lower, which is good. You want the denominator to be low. And then, but the main hit is it's over twice as expensive. So two times is more, over twice as expensive for only 20% faster for protein generations. And again, that's not even counting all the other time loading. But if you get up and running, then you don't have to, keep loading. It's just every time you disconnect and then hop back on. So the summary with this is basically use the V100 high RAM. The trend is most of these notebooks are either set to run best without GPUs or with GPUs. Now, this one was actually set to run best with a GPU. And I didn't try the T4 because I knew it'd be slower. And I tried a TPU, but it's, like I said, it was the way the code was written, at least, with mine, as, that didn't work. So just stuck to the GPUs. And it's also, so protein generation is very practical. Now, what was presented today is just a sliver of just the possibilities of generative AI with proteins. So again, the main conclusion with this is basically you generate, these, from a previous database that's more familiar, and then the more specific one based on force pooling with atomic force microscopy in the lab. Based on that data, you generate these charts, and then the generated proteins should be as close to that as possible. So of the three that I showed in that table, the 0.41 was a lot closer than the other two as far as pooling. So this is thought to be a lot harder than the other types of secondary structure, those types of things. And, so here again is the diagram. So this should make a little bit more sense at this point. So it's, again, you have to have some basis. So this is a strange case for me because most of the generative AI I run into is unsupervised, meaning that there's no labels to the data, and meaning, ChatGPT or whatever, generative AI that you're using, it's just figuring stuff out on its own. So this is actually generative AI with labels. So I believe this would fall under supervised generative AI. That's just how this one works. Typically, if you could do that, you can get your very best results because, you're defining what each of the labels are. It's not open up to, computers' interpretation. And obviously, the majority of the time when, these other models are spent also all over the internet, where this is just spent on proteins. Now, I want to cover a couple of these tensor networks, and basically there's big trends with it to use lightweight, and they're linear. So they actually linear algebra instead of using fully connected layers, instead of using convolutional layers. So the two models, like I said before, I believe in this paper, they both use convolutional neural networks, making it a candidate for a small, matrix product operator, matrix product state, and especially make it a lot more explainable because there's a lot less of the nonlinear connections, meaning a push towards what medicine is requiring. So this first one in specific was for image classification, and they've been working on it for a while with it. And I would say, this is 2021, but it's just an example of using a matrix product state with images. And I believe it's gotten better over the course of time. The biggest issue is not the efficiency. Tensor networks, if you can get it into a matrix product state with those algorithms, it's going to be efficient. It's the performance that's been harder to get. So anyways, this is an earlier paper. Now, this one I would say is definitely cutting edge because this is multiverse computing. They did a Llama 2 7 billion parameter, which, by the way, is now out of date because Llama 3 just came out today. But it's still, a huge, proof of concept that was proved to substitute, in those cases, transformer, multi-head attention, and one other layer, like fully connected, that type of stuff. So in this particular paper, they were focusing on convolutional models, right? So this is very similar to, the types of networks that are used in, the protein generation paper. But you're going to see that a lot because you're already seeing it today with TQ, or it's Terra Quantum, multiverse computing, and there's a third that goes with that too. But you see the tensor network layer going into this. And by the way, all of the previous research done by this company with Penny Lane and Qiskit is directly applicable to use with tensor networks now. So it's controlled approximations of quantum-inspired algorithms that, those are available to use too. I think the first thing, so this is basically where the company sits right now. So biochemical, generative AI, drug discovery, tensor network, quantum-inspired technologies, anti-cancer medicine, software development. So high-dimensional quantum biochemistry is basically, as we're watching this very interesting video this week, and it was a little old, but it just captured the essence, is if you have to use quantum mechanics, which is very, time-consuming, memory-consuming, for a specific binding site, those types of things, you would use it, hence quantum biochemistry. And what tensor networks do is basically they approximate some things that can be approximated so you can get to these bigger solutions. And I think the very first thing is actually going to be the model compression and explainability using lightweight and linear tensor networks, because it's more straightforward. And, it's been done with Llama 2, GPT-2 small. And, these are the core models to use. Is basically it's compressing them to very like 30% of their size, maintaining a lot of the performance, those types of things. And I mentioned the last one too, is when you have high rank data or like high dimension data, it's basically if you can get it into a tensor network form that's low rank. And by the way, they're coming out with new algorithms for tensor networks and then new solvers. So meaning like basically a broader spectrum of tensor network applications to science and medicine too. Are there any questions at this point? And I saw some people kind of hop in. And then feel free to put it in the chat as well. We'll stick on the slides for now. If you have any questions on any of the specific slides, a specific slide number, I could definitely go back. And then if you joined a little bit late, the two big conclusions is basically you use generative AI to solve a specific task. And depending on how hard it is the level of development is required. So something like a beta sheet, if you want a protein with an exact beta sheet or alpha helix, that's easier than having one that, generating a protein that would correspond to a certain pool, mechanical strength, basically, of a protein. And one thing I forgot to mention is this is really important for cellular activities, right? So you have to have specific, proteins of certain strengths and these types of things too. And it's one of the metrics, right? Because you can measure molecular weight, you can measure isoelectric values, which is basically, when is the whole protein neutral, whatever that PI is. And there's many ways to measure them. So the people will implement, Gen AI a lot more if there's not a regular substitute that exists today. So any questions regarding any of the authors' figures or my figures regarding to the protein generation? Yeah, we got a question here. I'm not quite sure. So this is Anastasia asked the question, in what time frame will this research reach its productivity plateau? Yeah, maybe if you could get maybe just a little bit more detailed. I guess my perspective is that it's still, getting a lot better. And like we're seeing kind of these leading papers in Science Advance and other papers too. Like the ESM2 model was a science paper. And, they're typically in big journals, like use Gen AI for tasks that, just aren't good at all to use with regular AI. Those types of things. So yeah, if you could get a little bit more specific with that. And then if anybody has any other questions. Yeah. Feel free to come on, because the way that I'm just reading this is, as far as a productivity plateau, or I guess what are you referring to is as far as like it's more accessible to more and more researchers, those types of things, like some drugs against cancer, those types of things. I think based on this paper, based on the author's previous papers, the two other, the AM1, the alternative methods, is that it looks like it's going to be a very definitive, Gen AI to create proteins for a specific purpose, whether it be end to end, or if it just has some, I think that you could do a lot of the solubility and easier tasks, but figure more of the kind of complex tasks with more data sets would require, additional like Gen AI. Like figure like it's powerful, right? Like it can learn on, unlabeled or labeled data. Awesome. Any other questions?
So hi, Kevin. Like nice talk again. And so I saw that I attended your talk last week, and that was also related to protein generation. This one is also in the same domain. But at that time, I didn't really understand, what was the significance of it. But this time, I probably understood a little bit more that you can generate the full protein, or at least the alpha helix level of geometries. So my question was, because it looks like the AI is doing all the work, why not to use the cheaper traditional methods after we got the sequence
Yeah,
to
so yeah, if you were to use like just traditional supervised methods, because as far as I know, all of the data was labeled, because I kept coming across that in the paper, and you don't always have to use Gen AI, if the data is labeled. So it's just but they're both patterns, right? Because if you just have, say, for instance, these fall under more like image, right? Like this is more like an image production. You're producing an image of a protein or these types of things like UNets or convolutional based neural networks. So yeah, I mean, if you were looking at it on the biggest scale today with all of the big LLMs, is they're obviously training off of unlabeled data, and that's thought to be the future, right? Because it scales, right? Because nobody has to actually sit and label every single website. The computer has learned through text or images and multimodal, like Gemini does multimodal over there, right? So I believe that there's a strong benefit that the authors used Gen AI for this specific paper as opposed to supervised learning. Because typically every other one that I've come across so far is typically, if you don't have labeled data, it's just a given. Use Gen AI.
No, so when I say traditional approaches, I'm actually talking about regular molecular mechanics that people use with, say, GrowMax or something else, right? Some force field that people just do with do any sort of geometry optimization or MD, whichever one people are dealing with. So now that they gave these initial structures, it would be ridiculous to ask an AI to give a good structure right away, because that's too much to ask. But at least that can be a starting point for for a normal optimization before any analysis is done on that structure.
Yeah, I actually think the biggest thing is the diffusion, right? Because like similar to GANs, where you're training off of just like 10% real images and 90% of the other image, soon to be images or noise. I think that's where the efficiency lies, and this falls under stable diffusion and these types of things. So you have your curve that you're trying to match, and you're starting with random noise, and it's that iterative process I showed in one of the figures. I think that is where it's at, because I believe that's a more efficient way of doing it as opposed to supervised. Supervised just in a traditional sense to try to generate something. And again, there's so many restrictions on all the other ones. Say for instance, BERT, which I covered last week, that's not typically generative. And then also with supervised learning, that's typically not generative either. So it's typically, unsupervised, generative, label data or not. So I think that's the key thing, right? Is that it actually gets to the point of generating the proteins, as opposed to like, I don't believe that you can do that with other types of supervised learning. Like that's
So,
like a de novo.
yeah, so you know, I mean, so I'm very new to this, AI based, molecular system generation, and these are really big, systems. But I've heard about, you know, in AI generation of small molecules. So, do these algorithms that we are seeing here, the language model based algorithms, do these generate small molecules also? Have you seen that somewhere before?
Well, the first thing, this ESM2, this
Mm,
Facebook model, it's language model that was used in the specific paper. It only uses a technique, as far as I know, it's called fill mask. So I've actually, further developed the fill mask. And it's basically if there's a blank in a sequence, based on what it was trained on, it'll provide that specific amino acid that would make most sense based on what it previously it saw. So that's just fill mask there. And again, with a diffusion model, I know because I've run, different diffusion model, and it falls under text generation. So the new Llama 3 that I believe came out today, if you look on Hugging Face, it'll say text generation. So I think that's the key distinguishing feature between a lot of the LLMs, is if it does, like a BERT model can do a bunch of other things, right? But it can't do text generation. But then like a GPT model or diffusion model can generate text, i.e. translate it into some protein information. And that's its unique thing. So I think that's the clear boundary as far as like with, text generation, unsupervised learning, or, these bigger LLMs that, it's able to generate something based on something, not just classify or object detection or, per pixel, image recognition, these types of things. It's actually taking something and completing a sentence, based on what it's seen before. So that's what I've seen especially in Hugging Face, where a lot of these models live, and actually that's where, this model card is for this specific paper, is that use fill mask for the first part, ESM2, and then their diffusion model is doing something with that data, but then generating, this new amino acid sequence.
thanks.
Yeah, and in part it has to do with architecture, because BERT architecture versus GPT, or diffusion. It's what it's been made to do or be best at. So that helps a lot, because if you get on Hugging Face, when you click on, specific models, in the upper left-hand corner, it'll show text generation, fill mask. You can do like text to image generation, text to video generation. There's some models that are specific. Now, however, some like Gemini, so trying to think, Google's Gemini, there's a bunch of notebooks out on their GitHub with this. You can take in text, video, image, whatever, and then it could still output. It's called multimodal, right? So that's another developing field too. But a lot of times it's based on architecture, as far as like the restrictions of, can it just do a bunch of these other tasks, or does it do text generation really well? And you see with this one, they use fill mask plus generation. Any other questions? Yeah, so these slides will definitely be up. Now, as far as the second question here for Wamika is for the current accuracy level, it depends on the challenge of the task. So if you saw, I showed, basically as far as an R² value, it was closer to, I think, 93 or 94 for, I think it was just protein unfolding. But for the force generation to try to match that curve with a generated protein and then test it, that was like 42, 43, but it was better than the other two ones that was like 0.1 or 0.2. So as far as like the direct application, I think that in all these cases, you're getting, these proteins that are definitely starting off with a lot more mechanical strength, or resistance to breakage or those types of things. And it'll likely only get better as far as, because you want, basically if you have a specific protein that you're looking for that matches this specific force curve, today that's a challenging task. But for Gen AI to do it today, 0.42 for R squared, it's not too bad, right? And compared to the other two competitors. But yeah, it just depends. It depends on the problem. It depends on how many times, if you go to generate a hospital image using something online or in your own notebook, it's seen a lot more development, I think, than, with proteins. So everything just takes time. Any other questions? And for those who's starting out, I would definitely run this notebook. It shouldn't be too hard to find. It's on, so I posted some of the results, I think, last night. And then you'll also be to see on this specific notebook as well. Click on their GitHub page and just download it. It should run out of the box using a V100. And like I said, I had issues with anything besides changing the number of proteins generated. It's a slider, it's set to 4, and you can change it to 8 or 6. In one of these in one of the figures that the author showed, they use 6 and 1. And then, for the big study, kind of like towards the end of that part of the discussion, they were using like 182 to see how close it was to the original curves. So yeah, it's cool. Occasionally you'll find stuff like this that, it's basically their paper running inside of a notebook. And you could see things as far as steps and epochs and things to change. And, you could definitely change, because I changed from V100 to A100, those types of things. But, for other things, it kind of like stick to the number of proteins generated. So any other questions? So anything related to Gen AI, I would definitely hop onto some other AI groups. Like this one's going to be mostly drug discovery as it relates to Gen AI. But there's like weekends, which is not the best for me, but there's a weekend, San Diego Advanced Machine Learning Online on Meetup. And then there's another kind of Kaggle machine learning group Sunday. Let's see, it'd be about 11 Pacific time here, so a little bit into the afternoon on the Eastern Coast. Did you have something new?
Yeah, so Kevin, you mentioned Hugging Face. I am not familiar with that, but
Yeah.
I just looked up, and so can you like guide me, maybe others? I don't know if other people are already familiar with it. There's so much stuff there.
Yeah.
How do we approach finding something?
The first thing you want to start with are called pipelines. Now, if you look at some of my previous posts on LinkedIn, or you could just search for pipelines Hugging Face, it'll pop up with some of these. And all you have to do, it's like 4 or 5 lines of code, like to say for a text generation. Copy and paste that into, the biggest things you have to import is usually Accelerator. So Accelerator is a Hugging Face, kind of like it uses GPUs to speed things up. And the other one is Transformers. So Transformers is Hugging Face essentially. So you import Transformers, and then from that, you might have to import something specific to GPT or BERT or those types of things. But it should be pretty easy to find. So you just search for pipelines. And actually there was, I think, an Assembly AI is the name of this group. I searched for it on YouTube, and they give a really good example. And that's what got me going. Their notebook was not good enough, but, on the Hugging Face with that. Now, the other thing is, because
everything, I would look at Hugging Face like this. What type of model is it? Is it multimodal? Like, can it do a bunch of different things like Gemini, like Google's Gemini? More often, you're just going to run into like text generation. So in the upper left-hand corner, there'll be like a button, it'll just say text generation. And that is the specific type of task that model does, okay? So if you're trying to create an image, but you're stuck in text generation model, that's not going to be the right model for you. Now, the other thing that helps beyond the Hugging Face pipelines page is if you scroll down in the model cards, a lot of times, so say if you typed into Anoop or anybody, if you typed in like Prot GPT-2, which stands for like protein, generative pre-trained transformer 2, it's an open AI base model that was retrained on protein data. That's a good model to start with. And if you scroll to the bottom, so after you put in Prot GPT-2, it'll give you like 3 or 4 good examples, and you just copy and paste those 4 or 5 lines of code. They're going to be simple tasks, right? So it's going to be like, for my, basically generating a new sequence. And I have a couple of these up as well. So in my drug discovery folder, you can play with these models because a lot of them are based on that, on these model cards. So you'll see the one from today there too. But if you want to start off with something small that works, the Prot GPT-2 or Prot BERT. So again, the Prot BERT is a BERT architecture, so it's not generative. So that specific one does fill mask. So fill mask was also used in this paper too. So fill mask just puts in another amino acid that's missing. And I think you can use it in different ways, but it's not a generative model, right? So that's the biggest thing, is find out what you want to do. And again, I have a bunch of different, it's there in my Hugging Face folder there too for code. Yeah, there's 3 of these that are all pretty helpful, and they all should run. And find out what you want to do. Like, okay, is this for work? Good. Like it does this. Okay, I need to generate an image. I did one that was a text to image. It says text to image Gen AI in that second link. And I gave it a simple task. I said, doctor helping another patient. And then I could run that so many times. And then I created a nice picture of that, say 3 of those images generated from that text. And then another one might be medical AI is very, and then you don't finish the sentence, but it's left in quotes, okay? And then the answer, some of them says medical AI is a very early field because the data that it was trained on, like GPT-2, was several years old. And then other one says it's a very helpful field, right? So it just depends on the data that it was trained on, how big the model is. So typically the bigger models will give a better response, those types of things. But I would really get onto the level of doing it in notebooks as opposed to going to different sites. And a lot of times if you optimize it, say I could generate a nice 512 by 512 image, work related, and then that one, I could generate in 2 seconds with an A100. Now, if you go to use somebody else's website, they're going to be using like a T4 or something below that, like an old GPU that'll take 10 seconds. However, with you, you have to load it. You're going to have to load the GPT-2, which will take a little bit of time. I think it's like 180 million parameters, but it's not like massive. So yeah, that's my recommendation, is basically start off with the task you're trying to do. The text to video stuff, it's a pain unless you have awesome hardware. And I was getting back like Shutterstock kind of, it wasn't really even generative. It was just like stuff on Shutterstock that it was probably trained on. And then to get up to the good quality with the video stuff, you're talking significant time and you're talking significant hardware, right? So things that might make more sense are like text to speech or those types of things.
Yeah, I'm not looking for the video or audio or images. I'm mainly looking for like uh, you know, structure generation. So
Yeah,
at least like the sequence that you saw today, you have these amino acids, but in case of say atomic things, then these can be smiles. So I'm talking about something like that, where there's a starting point that is generated from AI, and then we can deal with the smiles and move from there.
yeah, yeah. I would say, I mean, for instance, with the example from today, with the R squared at 0.41, which is better than the other models as far as when you generate, I think it was like 182 of these. So that's a good data set. It's still not 100% where it's generating that exact protein, because it's diagnostic, like an alpha helix. Every time you kind of stretch that out, it'll be sharper. It's going to take more force, a lot more force than a beta sheet, those types of things. And I think they'll all get better. So for instance, the ones that I put up here, between drug discovery, Hugging Face, is that it would generates the sequence, and then I would compare it to the isoelectric point, molecular weight, perplexity. Perplexity is really interesting because it's a term, I think, just for in protein space. It's basically saying like, well, how well was it utilizing the trained data that it was trained on, right? So if it's very complex, means that the answer that it came up with was not heavily based on what it was trained on. So in one of these, I think it was GPT-2, they says we don't have a really good metric. We just know generate a bunch of proteins and then pick the one that's least perplex, right? So all this stuff will likely keep getting better. And I think the biggest development, because besides this paper, was Llama 2, and a lot of things are going to be switching to Llama 3. So this is basically Meta or Facebook, and Llama 2 is pretty open. And one of the papers, they actually did a tensor network substitution on. They did it on Llama 2, 7 billion parameter. Now they just came out with Llama 3, 8 billion and 70 billion, I think, to not confuse the 8 and the 70. So this is a text generation model, and that's typically kind of like the cutting edge stuff. And you just can't go wrong with text generation to start with. It's very powerful. It can be converted, obviously, to doing protein sequences and bigger proteins, that type of stuff. So
Thanks.
yeah, and just watch a ton of YouTube videos. That's always a good thing to start off with, because I think many researchers, you start off and you pivot to a new area like AI and you want to apply it to proteins, is you just get afraid. You just say, I'm never going to get there. But in fact, if you do small things, like say you can have to watch some videos, but you just chip away, right? So watch a bunch of videos, read the papers, and then generate something on your own. And that's going to be a much more than if you work with other people in your field that don't know anything about it, right? And then you're going to have to fully or further develop it. But there's certain things and say good ideas that only come out when you're, developing something, or you give a seminar that's like a work, or you you put up a model, that's further improved. That's another work, right? But it's a slow process.
Mhm.
And then anybody else that we haven't heard from? So, and it's perfectly fine if you have just general AI questions. Now, the reason why, because I go to these other AI groups, and one of them says that by the time you go to deploy a model and click play, it's already out of date. Now, Llama 2, I think, came out last year, 2023. This is in the headlines, by the way, today. And then Llama 3, or April 18th of this year. So figure at least once a year. And they say at least 10% better performance. And they said with 8 billion parameters, you could do some things that the previous Llama 2 70 billion parameters couldn't do, right? So you do have to stay up to date.
And if you want to run some other stuff, Gemini, which is Google, they have a ton of notebooks up. Just search for Gemini AI notebooks in Google search, and then it'll be the top hit. Obviously, you're using Google, and then just go to that directory, and it's all kinds. But what Google's basically saying in all this is basically they want a foundation model. And that foundation model can take in speech or text or images or video, and it can output the like too. And, the models that they have up there, they have that kind of like feature, basically, is that, you're not limited to just text generation or just whatever. But it's a type of thing. It's like if you have a really good text generation, like a Llama 3, likely, because Llama 2 is pretty good, is that you'd probably stay, and you only want to use text generation, you might just stay with that because you're not attuned to the other parts of the architecture that you don't need, or you're loading too many parameters that you wouldn't be utilizing, that type of stuff. But that's Google's take on it, is with LLMs, is to have a single foundation model and then use all these different data types to it, as opposed to the more fragmented, oh, do I want to use, like a CNN's better for this specific case, or transformers better, or vision transformers better for, classification, or those types of things. So you're going to see that trend too, is try to unify everything with LLMs, and they'll keep going higher with parameters, and then the hardware will keep going higher. And that's the battle, right? Like if people put up like an 8 by 7 billion parameter, which is 56 billion, for most cases, for you and I, like consumer stuff, that takes forever to load. Like it's literally like 8 of these Llama 2s that has to load before you can do anything. So awesome. Anybody else that we haven't heard from? And, just don't give up. Don't give up on Gen AI. And whatever your state is right now, just know that if you're working hard on it and like developing stuff like code, or, teaching people too, like the Feynman approach, those types of things, is you'll start to go into new layers or new levels that you didn't think that you can get to. And, it's the whole thing of like doing stuff. It's not just reading papers. It's not just watching seminars. It's, just doing something with that afterwards. Awesome. And any other kind of last questions or comments? Yeah, well, this is an encouraging comment. I actually really like this one. So Anastasia says, I can write a transformer, which is awesome, but I don't know how to use Hugging Face. I would be glad if you tell me at what meeting you told this. Oh, okay. Well, just basically the crux of it, transformers make up the majority of the LLMs, and anywhere from GPTs to other things too. So hence generative pre-trained transformer. And it's really not that hard, but yes, you can watch some of the previous videos. I'll detail it more. And kind of like what I said before is like, start with the pipelines, Hugging Face pipelines. And the only thing you have to change in between the quotes for the model name is the name of the model. Now, when you copy and paste from Hugging Face, you have to include the author's name. So there's a copy button instead of just scrolling over with text. And then in your 4 or 5 lines of code, just paste it in there. And I was able to do that basically 30 different experiments, going through, say, some tasks were more sentiment analysis, like easier stuff. And then another one was summarization. And then obviously the text generation ones, the models take longer to load, but there's a lot of different models out there to choose from. So yeah, and I would say, watch some YouTube videos as well with it. And you can watch the previous ones of these too, because I definitely touch on that as well. Awesome. Any other last kind of questions or comments here? And I appreciate everybody coming on. So this has been Event Seminar 131, Thursday, April 18th at 3 p.m. for Drug Discovery Gen AI and de novo proteins. Have a good rest of the night and have a productive rest of the week. Take care, everybody. Bye.